Okay, now let's try out a problem that is going to deal with wedges. So a wedge is something that uses the mechanical advantage of its small slope to lift a comparatively large weight. Now, in this problem, our wedge is considered to be weightless. We're not going to worry about that. But we have this 200-pound weight, and we're trying to figure out what is the force P such that motion would impinge up the hill. What's the force P that motion would impinge up the hill? In this case, I'm going to say that our coefficient of friction for all surfaces is 0.4. Okay, there we go, 0.4. Now, this is not an easy problem. It has a lot of steps to it, so please follow along. It's not terrible either, it requires quite a bit of free body diagramming, which nobody necessarily likes. So first off, let's look at it as a whole. Well, since I'm pushing with P, there's going to be a force on this wall that says, I don't like that. It's going to push back. So I'll call that normal force 2. I'll have one right here as well, which will be normal force 1. Also, if motion is impending up the hill, there's going to be a friction, which will be frictional force 1. And there will be a friction right here, which will be frictional force 2. Okay. We also know that since motion is impending, that all these frictional forces, they've reached their max. So that makes things a little bit simpler. Okay. I believe this all looks pretty good. Now, how many unknowns do we have? Well, 1, 2, 3. And immediately you rejoice and say, oh, thank goodness we don't have to do any algebra. Because this has a size, right? And it's, but wait, where's all the dimensions? Do you see any dimensions here? You don't, which means we have to consider all this to be more or less a particle. Yes, there will be algebra. Makes me think sound like There Will Be Blood from that movie years ago. But there will be algebra. Okay, so let's get to it. First off, we're going to go ahead and write out our equations for this one. So we're going to have sum of the forces in the x, and it's going to be equal to P. And what's going to be pushing back on it? Well, minus N2, okay. And then both N1 and my frictional force are going to have a component that pushes against it. I need to be very careful here because this is a 30-degree wedge, but it's only 15 degrees from the horizontal. So that would be 15 degrees here, and that would be 15 degrees right there. Okay, so with that in mind, I would need the sine of this one, because it's the opposite side over hypotenuse, and cosine of this one, because it's going to be the adjacent over hypotenuse. So minus N1 sine of 15 minus 0.25 N1 cosine of 15. Okay, now that's going to be equal to 0. Now we need all of our equations we can get because in the end we're going to have to try to solve these. So now let's do our sum of the forces in the y direction. Now when I do that, what do I get? Well, sum of the forces in the y is going to be equal to, well, I'm going to have my N1, but now instead of being sine of 15, it's going to be cosine of 15. And my frictional force is actually pointing down, if this is my positive direction. So I'm going to have minus N1 sine of 15. So we switched from cosine to sine and from sine to cosine. Other forces we have are going to be the weight and the frictional force up there. Whew. That is a whole lot. A whole lot. But this does allow us to solve for either N1 or N2 in terms of the other. So we should probably go ahead and do that. So let me go ahead and get this typed out and we'll see how it comes. So first off, 15, and I do cosine of that. It's going to be 0.965. Okay. So I'll go ahead and write these down over here. we go. And let's do sine of 15 now. So we 0.259. Okay. So then if I want to simplify this equation right here, what I will get is that n2 is going to be equal to, and it should be equal to the following. Okay, so that would be cosine of 15, which is 0.966, minus sine of 15, which is 0.259 times the coefficient of friction. Okay. That works pretty good. And now I'm going to divide by the coefficient of friction. Divide by 0.25. Okay. So I get that it's going to be equal to 3.6025 in 1 plus, I'm going to have the weight in there as well. And what will I get? Will I have weight? Actually, minus 200, but that 200 was also divided by the 0.25, which makes it 800. Okay, so I get this equation right here. So that's one. It's not enough to solve, but it is something. If I want to, I could plug that into my earlier equations, and I would get something like this. So I would get that P is equal to 3.6025 in 1 minus 800. And let's see, plus 0.259 in 1 plus 0.25 times 0.966, 0.2415 in 1. Okay. So have a look at all that equation. I can simplify it a little bit more. So I'll go ahead and simplify that. And I get 3.6025 plus 0.259 plus 0.2415. Okay, so P is equal to 4.103 in 1 minus 800. Okay. 4.103 in 1 minus 800. Woo! That was a whole lot of algebra there. I've got a nice little equation that's looking good. If I can solve for n1, I know what I need to do. Okay, so let's go ahead and set that right there. P equals 4.103 in 1 minus 800. I'm going to write that up at the top. So as soon as I can solve for n1, I can come back to it. And n2, I'll go ahead and make that, bring the equation up there as well. Actually, I plugged it in. Wait, don't worry about it. Okay. Now that I've done that, I'm out of equations here. I still haven't solved, so I'm going to have to break it up into individual 3-body diagrams. So I'm going to take P right here, and just look at this one. This is my little wedge. It's 30 degrees. I still have my normal force 1, just like before. I still have my frictional force, just like before. But now I have a new one. I have this contact force in between these two objects. Contact force in between these two objects. So I don't even know what that is though. So I'm going to have to make a new one, which is going to be call it N3. And similarly, there's going to be a frictional force for N3. Okay, but if I look at this, can I solve? And your initial thought is no, because I've got P here. That's 1, 2, 3 unknowns, but we still have our earlier equation. Don't forget that. The earlier equation is there. And it's only in terms of P and N1. So I do believe that we're going to be able to solve. So let's try it out. First, let's do some of the forces in the y direction. Okay, so both my frictional components and my normal components are pointing the y direction. So I can do that, and what I will get is that, let's see, make sure I'm very careful here, that's 15 degrees, that's 15 degrees. It's going to be equal to n1 cosine of 15 minus n3 cosine of 15. Okay. And then we're going to have plus 0.25 n3 sine of 15 and minus 0.25 n1 sine of 15. It's all equal to 0. And hopefully you see that these are identical. They're just pointing opposite sides. So for this to be in equilibrium, these forces would have to be equal. So if we solve all this, what we get is that n1 is equal to n3. Okay, that's good. Let's put it up here at the top so we don't forget it. Let me make sure I actually took my signs. I did, they're all the same. So now that I've done that, let's do some of the forces in the x direction. So once again, everything has a component, but now we know that our n3 is the same as n1. It's got the same exact load. So let's try it out. And also that won't always be the case. This is a nice symmetric wedge, and it's, the way we chose our axes, it works out fine, but that will not usually be the case. Okay, so I have P minus n1 sine of 15. Okay, and then minus 0.25 n1 cosine of 15 minus n3 sine of 15 minus 0.25 n3 cosine of 15. Okay, all that's equal to 0. Well, we already know that n1 is equal to n3, so I'll just go ahead and replace that. And I think we can simplify quite a bit. So I'm going to go ahead and add all those up in my calculator. Okay, so what do I get? Well, I get a lot of stuff in here. 0.259 plus 0.25 times 0.966 plus 0.259 plus 0.25 times 0.966. Okay. Oh wow. It's not be pretty much 1. That's pretty fantastic. So we get that P is equal to n1. I'm a bit worried about my math there, but you know what? I'm going to take it. Okay, P is equal to n1. So, going back to my original equation then, what I'll have is that P is equal to 4.103P minus 800. And if I subtract it from the other side, I get negative 3.103. P is equal to 800, or negative 800. Whew. And if I solve, P is going to be equal to, let's figure it out here, 800 divided by 3.103. That'll be equal to 257 pounds. 257 pounds to move this upwards. Okay. Now this might have confused you because you're like, wait a minute, wasn't that wedge supposed to help us? Why is this load more than the weight? We're having to apply more force than if we just lifted that weight directly. And you're correct. We do have to apply more force on that little wedge to get that block to move up than if we were just to try to lift the block. Reasons you might do this. Well, one, might be easier to apply a horizontal force than a vertical one. 2, you might be able to use a hammer to apply that force very, very quickly and smack it and make it move upward. And 3, I more or less made this problem up as I went, and the fact that I added friction to the wall. In the original problem, it didn't actually have friction on the wall, which changed our numbers. Friction is a factor, and the friction here is actually making it more difficult for you to lift that block. It's making it more difficult for you to lift that block. So if we didn't have friction there, we would actually have a much simpler system, and it would have been more easy for it to lift up there. So it really just depends on your case. Either way, you've seen the steps to solve these kinds of problems. It involves algebra, and if you're lucky, everything works wonderfully. If you're not, you're going to have to do quite a bit of algebra like I had to do today. But it wasn't too terrible. Just break things apart and you'll be able to solve it. So thanks for listening, and I'll see you all next time. Bye-bye.